Yeah, so thank you. Thank you for the invitation to come here. It's always a pleasure to talk about what we are doing at T-Labs. I think this is a very nice presentation to wrap up the workshop because it shows already that large-scale network operators are already somehow testing entanglement over field deployed fibers. So many of the concepts that we've been discussing over the past years, decades, are now starting to get to the streets, yeah, going through the fibers and urban fibers. Yeah, and that's what I'm going to talk about today. Some is a summary of experiments that we have been doing in Berlin. Yeah, distributing entanglement. Yeah, from the quantum lab, the streets of Berlin. Yeah, and the thing I want to say before I start the presentation is that we are a group of let's say telecommunication engineers trying to understand the concepts of quantum mechanics, of quantum communications, and trying to make them real. Yeah. So if I could ask you if you could guess what's the biggest asset that a network operator has. So one of the biggest assets of a network operator is the optical fiber infrastructure, right? So DeutschTelekom, for example, has more than 800,000 kilometers of optical fiber cables deployed across Germany. That's around 20 times the circumference of the Earth. Yeah, and and the company is still working on very actively on rollout. So we have now 10.9 million households that have already fiber connections up to 2,000 megabits per second, and we are planning to reach a number of 41.5 million households until 2030. Yeah, so that's a big asset, and we are looking forward to generating more revenue streams out of this fiber network. Yeah, and we are entering the quantum internet era, and we want to generate revenue out of quantum services. Yeah, so that's the reason why we want to build the quantum internet, and this network that will send, receive, and compute information encoded in the quantum states. And for what? What are the services that we kind of envision in the quantum internet are for security, for example, distributed quantum computing, improved sensing capabilities, and more accurate time synchronization. But we have this big asset, but it's somehow tricky to use it sometimes for quantum technologies because this fiber infrastructure has characteristics that also bring challenges. One of the characteristics that's that we have been deploying this fiber since the late 90s. Yeah, and we are still deploying new fibers. So there is like a combination of legacy plus modern networks. Yeah, so for example, if you are thinking about in the future routing entanglement in your network, you need to distinguish between good and bad fibers. I usually like to show this plot here that shows a fiber that was an LTDR measurement that shows a fiber that's not that old. Yeah, that has an average loss of 0.28 dB per kilometer, but have also fibers that coexist with the system, with this network, that have a much worse loss. Yeah, for example, this yellow curve shows a loss of 0.4 dB per kilometer. We have other factors such as the fibers, they are subject to external factors, yes, external agents, like the technicians that are touching the fibers. We have the fibers that are deployed in the field, so they change the temperature of the fiber, change the length of the fiber, so they contract when it's cold, they expand when it's warmer. We have rats also walking in the fiber ducts. Yeah, they're chewing the fibers, they're touching the fibers, and this causes, for example, unstable qubit transmission. Yeah. So as an R&D team, we want to know, we have the idea that if we want to integrate quantum technologies into traditional communication networks, that requires to understand how to efficiently transmit and how to efficiently receive qubits, or in this case, entangled photons. That brings me to a short overview of this presentation. So first of all, I want to go through some of the basic applications of entanglement. Yeah, why we see entanglement as a resource. So basically for secure networks, distributed quantum computing, and precise time synchronization. And but I think that the main focus of this presentation are the challenges that we need to face in order to distribute entanglement, for example, in field deployed optical fiber networks, and what are the solutions that we have seen so far, and what are the possible solutions that we kind of envision for the future. And then I would like to wrap up with some takeaway messages. So, yeah, so the entanglement has a strategic importance. Yeah, it's not in vain that we see many companies, large-scale companies, investing and showing demonstrations, the POCs with entanglement. We see Cisco inaugurating a quantum lab in Santa Monica, already launching a quantum networking chip that's quantum source, basically. SoftBank in Japan also doing quantum internet demonstrations, over optical fiber cables, and DeutschTelekom here in Germany as well, showing the first steps into the quantum internet. And as I mentioned before, the telecom operators, they own the fiber infrastructure where the entanglement distribution must happen, and with that we have this great potential to generate more revenue streams. Yeah. And as an R&D team, we try to understand, the role of DeutschTelekom as a provider of entanglement-based connectivity, because we believe that entanglement is the basic or the fundamental connectivity element for the quantum internet. At the end of the day, where can we use entanglement? So that's not very much new. You guys already know, for example, for quantum key distribution, BBM92 protocol, you have, for example, a quantum source that is delivered by DeutschTelekom in the future, for example, in Hanover. It distributes entangled photons, to our offices in Berlin, and to our offices in Bonn, and then we can establish, for example, secure communication. In this case, for example, the BBM92 protocol, you would see coincidences between HH detectors, BV detectors, AA, and DD. But we have problems with that. So QKD has this limitation in terms of distance. In this case of the BBM92 protocol, I think the longest distance was 248 kilometers using optical fiber cables. But at the same time that it suffers with this limitation challenge, the entanglement also provides a solution, which is building the quantum repeater based on entanglement swapping. So the idea here is that instead of having one source, you have two sources. You interfere one photon from each source with another photon from another source, and then you entangle the photons from Alice and Bob. And then this system is scalable. You can build a quantum repeater by concatenating multiple quantum sources, such that you can create like a very long quantum link, such that Bob and Alice can someday do QKD with each other. Is entanglement only useful for QKD-based applications? No, that's why we believe that there's a lot more to be explored beyond QKD, and that's what we kind of endorse. A telecom, for distributed quantum computing, that can be done by means of teleportation protocol. So we have an Alice. She performs bell state measurement with the quantum state from Alice with one of the photons from DPR source. Then you transmit the other photon from DPR source, apply a unitary transformation, and then the state from Alice can be teleported to Bob. Another thing that we are investigating experimentally at T-Labs is also quantum-based time synchronization. This is a very simple scheme. It's called the round-trip quantum-based time synchronization scheme, where you have a server, where it's the Alice in this case. It provides entangled photons. One of the photons is transmitted to the Bob side. So there it's either measured or reflected, and by doing some mathematics with the coincidence measurements between the time taggers, you can, for example, extract the time offset between the clocks of the server and the user. But in order to apply or in order to be able to build all these applications, we need to reliably distribute entangled photons over real optical fiber networks. And are there challenges in distributing these entangled photons over classical optical networks? There are. One of them is polarization drifts. So first of all, why we want to work with polarization? Because it's easy to create, to manipulate, and to measure. You can basically manipulate polarization only using linear optical elements. Yeah? And it's also a bit more compatible with atomic and ionic systems for quantum memories. Yeah? So what's the challenge here? Yeah, so let's suppose we have an ideal optical fiber, no birefringence. The fiber is extremely symmetrical. Yeah, so if you have an input state like this, so you should expect that the output of the fiber will show an output state like this without rotation. So what you have at the input would be exactly what you have at the output. Yeah, but the fibers, they are not ideal. Yeah, so they are subject to mechanical stress caused by bending, vibrations, twisting, and handling. Yeah, and these mechanical vibrations or this mechanical stress can induce birefringence, and this birefringence cause a rotation of the polarization. So let's suppose now that we have this input state here. Yeah. So it goes through a section of the fiber where there is a mechanical stress, it's caused by refrigerants, and then you get a rotated qubit at the output. The question is, how bad are these polarization drifts? So that's something that we characterized. Last year, we did a short experiment using our Berlin fiber testbed. Yeah, so we basically have, this is a classical light source here. Yeah, we send this classical light source with a fixed polarization state over our fiber loop, 50 kilometers, connecting us at the Winterfeldstraße to one of the nodes of the Berlin testbed, which is at the Humboldt Uni, the southwest of Berlin, 50 kilometers of fiber loop. And then we measure the Stokes parameters, for example, over 12 hours. Yeah, and as you can see here, the red, the green, and the blue curves, they represent the Stokes parameter, and the magenta curve represents the fidelity of the photon in comparison to the initial state that we had sent. Yeah, and as you can see, the fidelity fluctuates a lot, and the lowest that it can reach is about 87%, which is relatively low when you're talking about quantum internet protocols like teleportation. If you want to perform the state measurements, you need fidelities as high as 99%. Yeah, and how do these polarization drifts affect our entanglement distribution? So now let's suppose we have a very simple illustration. You have an ideal fiber here where you send one of your photons from the entangled state. And the other photon goes through a very, very unstable fiber where that's subject to a mechanical stress. So the photons travel over the fiber. The first one stays very stable over the transmission because it's an ideal fiber, but the other one gets rotated. Yeah. So basically, we perform a rotation of the components of this photon, such that the state HB becomes HB plus yeah, so basically a rotation to a diagonal state, and also for the previously vertical state, we rotate that to a diagonal state, such that at the end of the fiber, you get like a mixture of Bell states, so you don't have like a maximally entangled state anymore. So if you perform, for example, a CHSH test here, you won't have S value, a Bell parameter of 2.8 something, which is the maximum violation of the Bell parameter. And this happens because the fibers are unstable. So we tested this, for example, in our network again, how the entanglement behaves over long term. So we did this test with a commercial solution. So this is an entanglement source from QNect. So it's based on spontaneous for wave mixing. It's a bichromatic source. It generates entangled photons at different wavelengths. One of them is at 1324, our telco photon, the one that's going to be transmitted. And the 795 photon is measured locally. So we perform this measurement. So the signal photon, the 1324 nanometer photon, is sent over the network, and received back, and we perform a CHSH test to evaluate the violation of the Bell inequality. In this case, we don't perform any compensation of the polarization drifts. We just let it run and let it drift to see what happens. We performed that over a 30-kilometer fiber. That's a fiber loop from our office at the Winterthurstraße to another office at the DeutschTelekom, also in Berlin. Yeah, so as you can see here, the bell parameter, after approximately, at the very beginning of the measurement, we get a very clear violation of the bell inequality with the bell parameter of 2.75. But as the time passes by, after approximately 4 days, we reach the classical limit, right? Because of these rotations, this polarizations drift such that it misaligns actually the entanglement in the fiber, and you cannot achieve a maximum violation of the bell inequality. Yeah, so this is after approximately 7 days, you are already below the classical limit. But there is a solution for that. So it's basically applying automatic polarization control. So this is the system that we use. It's also a commercial system. Yeah. So the idea here is that you generate a classical pulse, with a very defined polarization states. And so that you see the representation of the polarization states here on the pointer here. So the system is composed of two boxes, the injector and the compensator. So the injector generates this classical light. So you perform like some type of time multiplexing. You either send your quantum signal or your classical information. And then when you send your classical information, so there's an interruption of the quantum signal, but this compensator knows what it should receive. So if it receives something bad like this, a rotated reference signal, it performs a feedback loop here and tries to revert back to what it was supposed to be received. Yeah. So we performed the same experiment as before, but now we add this APC system. Yeah. And you see here, so this is also, as I mentioned, a commercial system from Connect. As you can see here, so when we switch on the system, the bell parameter goes immediately up. It shows a clear violation of the bell inequality, and it stays over 17 days with a value above 2. We have a mean value of 2.5, and when we measure the mean fidelity over this 17-day period, we have like 99.34%. Yeah, so this is one of the problems that we need to face, which is the polarization drift. And when we are thinking about, for example, routing through different paths, to different fiber paths, we have to take into account that one route in one of the fiber network doesn't induce the same rotations as the other route of the fiber network. So, for example, that's what I'm showing here. So the rotation, the route 1 is different than the rotation of the fiber in the route 2. So when we are, for example, thinking about receiving entangled photons from a node and this entangled photons being dynamically routed, for example, we need to have schemes that can compensate that dynamically as well. So we did another experiment testing in our Berlin fiber network. So basically switch, with an optical switch, the entanglement distribution between this loop here, 15 kilometers, and this loop here with 30 kilometers. And so we do that every 20 minutes, for example. As you can see here, this is the first measurement, the second measurement at 30 kilometers, the third measurement at 15 kilometers, the fourth measurement at 30 kilometers. You see that you can maintain a very stable entanglement distribution with S value over a period of 14 hours. And you can see when you look exclusively at the classical fidelity, the fidelity that's measured from the classical light, you can see that when you're performing the transmission over one path 1, the fidelity stays very stable over the period, over 20 minutes, for example. Then you switch, you let it run for a few minutes without compensation. Then you perform the compensation, it goes up close to 100%. Then the entanglement distribution stays very stable for the path 2 and so on and so forth. But you can see that there is an alternation. So it means that one path, the compensation from one path is different than the compensation from the other path. Yeah, so the last problem that we have to deal with is classical noise. So there, at Telecom, we believe that if we want to build quantum networks, quantum internet, we need to use the field deployed fibers. Okay? And for that, the C-band is already occupied by classical channels, so we need to use other optical bands and multiplex the quantum channels in other optical bands. So far we have been testing, for example, the co-propagation in the C-band, the classical channels in the C-band, in the quantum channel in the O-band. Yeah. The challenge here is that we have to we have to live with the leakage of noise from the C-band into the O-band. But there are some other disadvantages as well when we are performing entanglement distribution in the O-band, is that we have more loss. Yeah, if you can see here, so in the O-band you have a higher loss than in the C-band, but on the other hand you have less chromatic dispersion, which causes a broadening of your pulse. So you at the same time you gain in terms of visibility. So this is one of the things that we performed. We created like a commercial 50 gigahertz channel here in the C-band by doing some channel loading, so to say, multiplexing that with our quantum signal, performing this transmission either over 30 kilometers or 15 kilometers. And we changed many of the characteristics of the classical channel. So we basically increase the power of the classical channel and try to analyze the S value. Because at some point it's impossible to see you have so much noise from the C-band leaking to the O-band that you cannot see a violation anymore. Because basically of noise. But you can see that there's a trade-off, right? So you basically, the more power you put in your classical channel, the less entanglement that you start seeing in your O-band channel. Yeah, we also tested some different frequency allocation schemes. Yeah, so in this case, we don't see a big influence of the frequency allocation. In this case, it shows an advantage because we basically are very, very far away from the O-band. So moving your channel around the C-band doesn't affect much the entanglement on the O-band. The last experiment I want to show here is that everything that I had done before was with channel loading. Basically, we were shaping ASE noise and emulating a classical channel, but we also have been testing that with commercial transceivers. Yeah, with this ADVA transceiver here, we also tested different power levels, and you can see here that you can tolerate a bit more of power. Yeah, for the single channel. Before, I think the maximum that we could tolerate was minus 1.5 dBm, basically because when you use these amplifiers, it adds more noise, like this noise figure, and it affects the maximum power that you can push up from your classical signal. But here, you basically see that the spectrum is basically flat. Yeah, you just have your commercial carrier here, and that gives a bit more flexibility to go up to 5 dBm, for example, for classical. Without crossing, 4 dBm without crossing the classical limit. Yeah, so this is the last thing that I want to show. Yeah, we've been pushing the limits, trying to see how far we can go with this O-band, C-band scheme. Yeah. So we also, as I mentioned, we have more loss in the O-band in comparison to the C-band, so that limits us in terms of distances. But we have been able to push that up to 100 kilometers of entanglement distribution in an urban fiber network. Yeah, from the P labs down to Strausberg, which is a nearby district from Berlin. So this is the maximum that we could achieve in terms of length in this frequency multiplexing. Yeah, so this is the result of the 100 kilometer over 78 hours. Yeah, so you can see that we can obtain L parameter very stable in this 78-hour period. So yeah, so my takeaway message is that if you want to build the quantum internet, we need qubit stabilization schemes, that can give us high fidelity and also long-term entanglement distribution. That's what we have shown here by performing this 17-day entanglement distribution in a urban fiber network. Yeah, and we can achieve that by using, for example, automatic polarization compensation schemes that can overcome the random and time-dependent polarization drifts, as well as the drift caused by routing through different routes, because each fiber path has a different condition in terms of polarization rotations. Yeah, and one thing that we've been studying is how to better design this frequency multiplexing scheme, because as the perspective of a network operator, we don't want to deploy a separate quantum network. We want it to coexist with our classical and optical network, commercial optical network. And we need to think ways of mitigating this crosstalk from C to O band. What comes next? So our team is planning to perform some experiments with the quantum teleportation to the end of the year. So we've been studying how stable we can maintain the entanglement distribution in our networks, but now we want really to test the quantum internet protocols in our network. And I think that one key step into the quantum network is really integrating quantum memories. So we are also planning to work with partners in this direction. Yeah, that's everything. Thank you very much.
Yes, thank you, Matheus. Are there questions or comments?
Thanks, Matheus. So my question is, when you show the results without compensation?
Say it again?
When you show the results without the compensation?
Yeah.
I mean, what does it mean without compensation? Because in principle, the polarization is not never going to be the same.
So the APC, let me go back. You mean these results here, right?
Yeah, when you are not compensating.
Yeah, we're just letting it drift. Yeah, so we want to show the drift that there is in field deployed optical fibers. If you don't compensate, this is what happens to your entanglement. Yeah, and if you compensate, this is what happens.
So how long is the fiber there?
How long? 30 kilometers.
Yeah, so you're never gonna get the same polarization that you put at the input, right? At the output, because of different effects. So does the system somehow calibrates at the beginning and then
we perform. Okay. Good question. So for example, from injector to the patch panel, for example, we have normal fibers. They're not polarization maintaining. So we do a manual calibration at the beginning. Yeah. So that's what we start with an acid that's very close to the maximum. We manually calibrate that. We save this reference inside the APC when we compensate. Yeah. And then when the APC kicks in, it knows what it should receive. Yeah. So it has already a saved reference, and then it tries to revert it.
Thanks a lot. That was a very nice talk. So I have a fair and unfair question. So when people started working, say, on QKD, all these effects that you have seen you're worried about, people worried about them back then, and they came up with pretty clever ways to compensate for them, like the experiment in Geneva, the plug-and-play QKD protocol. That was their way to deal with polarization by doing a round trip. And so when we think about the quantum internet, I think my feeling is that there's still a little bit of a gap between the community who says, let's build this entanglement sharing network, where the goal is to do what you're doing, like you're trying to offer this entanglement distribution with the highest fidelity possible, stability, and the folks who want to already do some protocols, who are willing to do, a bit more ad hoc things. And so there's, in my opinion, still a gap between these two. Yeah. And so to what extent, you're looking at it from the big network perspective, like to what extent would you be willing to get away from this kind of very clean network view and say, okay, I'm going to allow my network to be a bit more application defined on the fly. A network has some, maybe some software defined component that allows people to do something that's a bit more ad hoc for their application.
Yeah, but when we're talking about applications here, for example, quantum internet protocols, quantum teleportation, entanglement swapping, we need high fidelity, right? So we need to make sure that we can deal with this loss of fidelity in the network. So that's why maybe we are a bit delayed with regards to what people in academia are doing, probably, yeah. But that's part of, I think that's part of the evolution of the technology, right? So the academia develops, yeah. So the startup that we are working with, it's a spin-off from Stony Brook University, yeah. So develop the technologies, we bring them to our lab, yeah, and we test them, yeah. And I think this is actually the workflow for from bringing something to the lab to the real field, because I will not convince my boss to invest money to think about the concept of the quantum internet if I don't show that it's stable. That's how we somehow buy we convince our bosses in order to invest and to believe that this is the technology of the future.
I mean, that was it's a great answer. I mean, I think I'm just wondering whether, we have these 50 years of success of the traditional internet, and I think we're trying to map what has worked for the classical internet. But I think for quantum, things are a bit more fuzzy. Like, I don't think we can separate the applications from the networking as much as we could for the classical internet. And I mean, maybe it's a question for the whole group, but when you talk to funding agencies, they ask, well, why do you want a quantum network? And then you have to talk about the application, and there's a bit of a gap that we're struggling, at least I'm struggling to fill when you talk to people who want to see something concrete.
Yeah, we are also struggling with that, because that's exactly what you mentioned. So when we go to our bosses, they ask the same thing. Why do we need a quantum internet? Will it replace my classical internet? Then we say, no, it's a complement to the classical. So what else? Can I increase the network capacity with the quantum internet? Yeah, there are some ways, but it's not that straightforward. So it's hard, yeah. But this is how technology developed. The internet years ago, like 30, 40 years ago, no one believed that we would have like this networked world, yeah. So that we can share these presentation with people all over the world. Yeah. So there are more applications that we are not seeing right now.